Hello everyone, I am Dr. Fawzul Atik. I am giving some series of lecture on the course Probability and Statistics. In today's lecture, we are going to define what is probability. Then we will discuss few properties of probability and few examples we are going to solve. So, what is the probability? Given an experiment and a sample space, we already discussed about this. What do you mean by sample space? What kind of experiment we are considering in the previous lectures. The objective of probability is to assign to each event a number PA. To each event a number PA is called the probability of the event A, which will give a precise measure of the chance that A will occur. So therefore, this quantity given to the event A will measure the what is the chance that A will occur. Correct? And all probability assignment should satisfy the following axioms or basic properties of probability. Now, what do you mean by this axiom? This axiom means that some accepted truth, right? Without any proof that everyone accept that these things will happen. You do not have any proof. So regarding probability, we have certain axioms. Let us see that what are they. Axioms of probability. The first axiom, the non-negativity. For any event A, P of A should be greater than or equal to 0. So probability of any event is always a non-negative quantity. It can be 0, but it should not be it should not be negative quantity. Next is the probability of the entire sample space is 1. So because sample space is the set of all outcomes of an experiment. So therefore, that should happen anyway. So whatever outcomes happen, it should be fall under this sample space only. No? So probability of the entire sample space is 1. So this is always happen. And next is axiom 3, that is the additivity concept. For any sequence of disjoint event, A1, A2, so for any sequence of disjoint event, A1, A2, A3, and it can goes up to infinity. The probability of their union is the sum of their individual probabilities. So basically, this gives you the union of all the events, and that is the sum of their individual. That means it is P of A1 plus P of A2, and in this way it can go up to that infinite sum. This is the axiom 3. So these are some accepted truth. We do not have any proof, but everyone assumes that these statements are true in case of a probability. Okay. Now few properties in the name of proposition. So P of phi equal to 0. So probability of the null event, the event containing no outcomes, is always 0. This in turns implies that the property contained in axiom 3 is valid for a finite collection of disjoint events. See, here in the axiom 3, we have seen that this property is for infinite collection of events, right? So probability of union of infinite collection of events is equal to their individual probabilities, sum of their individual probability. So this is, the axiom is true for infinite number of events. But if you have this assumption that P of phi equal to 0, probability of the null event is 0, then this will also happen for finite collection of events, right? So that is a short proof of it. I'll just quickly show it how you can prove it with the help of this property P of phi equal to 0. So first we consider an infinite collection A1, A2, A3 up to infinite, where each of the events are a null event. Since phi is the null event, the event in their collection are disjoint. Yes, definitely they should be, because they do not have any event, any outcome. So they should be disjoint. So union of I equal to 1 to infinity, AI is again a null event. So because each of them individually are 5, so their collection is also 5. That means the null thing. And the axiom 3 gives you, because you know the axiom 3 is for infinite collections of event. So if you apply the axiom 3, you will be getting this. So this is the sum of this. Now, since union of I equal to 1 to infinity ai equal to 5, therefore P of phi equal to their sum, and that is equal to 0. And basically we get that collection of, like, sum of probability of ai, where each of the AIs are null event. So even if you take their infinite sum, it is going to be 0. So that thing, let us keep in our mind. And this can only happen if I have P of phi equal to 0. Okay. Now you take A1, A2, AN are any disjoint event. So they, one few of them may be null event, they may not be some arbitrary disjoint event. And in these events, add on to the infinite collection a n plus 1, n plus 2 up to infinite number. So in this collection, we are adding few more infinite number of null events. All of them are the null events. Then we have probability of I equal to 1 to ai. This union is equal to, I can also write that I equal to 1 to infinity ai. Correct? So their probability should be same, because last, after n plus 1 onwards, all of them are null events, so I can certainly write. But from here to here, I can easily apply the axiom 3. Axiom 3, I can say this thing. And then, because this is an infinite sum, and then the, for up to n onwards, it has some value, it may have some value, but after n plus 1 onwards, it is 0. So I divide this infinite sum into two parts. One is up to n, and after that it is from n plus 1 onwards. And therefore this part is 0. We have already proved it, and I can have this. So therefore I can have probability of union of I equal to 1 to n ai is equal to sum of I equal to 1 to n p of ai. So this we have already in axiom 3, it was there for infinite collection, but it is also true for finite number of events, disjoint event. I hope it is clear. Okay, now let me move to the some more properties. Now this is another interesting property of probability, that probability of an event, how it is related to its complement. So probability of the complement of the event E, probability of the complement of the event E is equal to 1 minus P of E. That is, you have a very easy proof of it. We can certainly discuss that, how we can prove it. Like I'll show you, we can easily prove this property. We'll quickly discuss them. Okay, just a minute, I will take a little deep color. Okay, now we know that for any event, the sample space whole is equal to E union E complement. Yes, definitely. And we also know that there is no common outcomes in these two events, E and E complement, because they are complement of each other. Now by axiom 2, we have P of S equal to 1, but I'm just writing the probability definition, E union E complement. Now by axiom 2, I can say P of S equal to 1, and that is equal to, now this is the sum of union of two mutually exclusive events. They are the disjoint event. So by axiom 3 and the property of finite sum, we can also say that this equal to P of E plus P of E complement. And therefore I can easily write down that P of E complement equal to 1 minus P of E. We can easily prove this property. So this is a property, we are going to use it in several times. We have the next property as this one. So if I have E is subset of F, then probability of E should be less or equal to P of F. Again, we can prove this proposition very easily. Let us discuss the proof. Suppose I have an event F, which is a little bigger set, and I have an event E here, which is a subset of F. So this is E and the whole one is F. Right? Now, my intention is to write this F, which is the union of two mutually exclusive event. So can I write this F equal to E union F E complement intersection F? Can I write this? Yes, I can easily write that because this is the whole sample space, maybe the S. So this one is the F and the smaller one is E. So I want to write F as a uh, union of two mutually exclusive events. So I can certainly do that in this way, that this is one part E, and also this part, which may be this part. What is that? It is E complement intersection F, right? So I can easily write that F is equal to E union E complement intersection F. Then I just apply the probability. So P of F is equal to, now these two are the mutually exclusive, so I can write their probability as probability of their sum. So P of E plus P of E complement intersection F. But this is a probability of some event. By axiom 1, I can certainly say that this quantity is greater than or equal to 0. Now, if this quantity individually is greater or equal to 0, so what can I say? Therefore, I can easily say that P of F must be greater or equal to P of E, which gives this property. P of E is less than or equal to P of F. I hope it is clear. Let me move to the next property. Now I have this property that is again a very interesting property of probability. How to prove that? Again, we'll do a similar kind of proof. So with the help of Venn diagram, we'll try to understand the set theoretic things. Suppose this is the event, this is the sample space. I have two events, E and F. This is E, this is the event F. I don't know whether they are disjoint or not, nothing is given, so I consider them, they may have some common outcomes. Right? Now, let us write that E union F as a union of two disjoint set. How to do it? Thus, like little bit similar way, maybe we can write down that it is the this part E and the rest of the part, that this part. How we can do it? We can write down that E union F is equal to E union E complement intersection F. And therefore, by axiom 3, we can write down P of E union F is equal to P of E plus P of E complement intersection F. Right? Now you may keep it that is equation 1. Now again, I can also write down F equal to the event F equal to E intersection F union E complement intersection F. How can I write? You can again easily see that. We can again see that this is the intersection part. This part is the intersection, and this part is the E complement intersection F. So therefore F can be written as in this form. And if I have this, again I can apply probability on it, and they are the mutually exclusive event. So it is equal to P of E complement F plus P of E intersection F. Now this value I can certainly get it from this equation, and I will put this value into the equation 1. Maybe I will write down again one more line. E complement intersection F is equal to P of F minus P of E intersection F. And therefore, if I put this value in equation 1, I will get the desired equation, which is a inclusion-exclusion identity for two event. I hope it is clear. So this is the proof that I have already discussed. Okay, so this is the formal proof. All details are written. Let me move to the some examples. Look at the first example and read the example carefully. Try to understand that and try to get the solution. You may make the video pause. Okay, it says that Joya is taking two books along on her holiday vacation. With probability 0.5, she will like the first book. With probability 0.4, she will like the second book. And with probability 0.3, she will like both the books. What is the probability that she likes neither the book? So this is very easy. We can apply the last identity and we can do it. So just denote some event. Let A is the event that Joy will like the first book. So I'm just write that AP. That is the first book Joy will like. A is the event. And B is the event that Joy will like the second book. Right? Then what other things are given? With probability 0.5, she will like the first book. So P of A is equal to 0.5. It is 0.5. It is also given P of B with probability 0.4. So I can write P of B equal to 0.4. And what is given? And with probability 0.3, so you like both the books. It means it is the intersection of A and B. So I can write down P of A intersection B is equal to 0.3. Now what is the probability that she likes neither the book? Now she likes neither the book. What does it mean? Now we all know that union is the at least, right? Union is the all collection, so at least one will happen. If I say that A union B, that means at least one will happen. So what is the P of A union B? Let us find that first. So first let us find P of A union B. And this event is that she will like at least one book. Now if I take the complement of this event, this probability, I will get the she will not like any of the book, right? Because this is at least one book she will like. So let us find the probability of this, and that all we know from the previous identity. It is equal to P of A plus P of B minus P of A intersection B. And if I calculate it, I'll be getting it is 0.6. Now she will like neither of the book. That means this event we have to get A union B whole complement, which is basically the this one earlier it was the at least you will like one book. Now if I take its complement, that means you will like neither of the book. And what is the probability of that? We all know the formula. It is 1 minus P of A union B. So one of the proposition, and it is 1 minus 0.6, and we can get it is 0.4. So we got the solution. Correct. So this example also we have proved it very formally. Everything is written. You can take a snap of it and you can have the solution with you. Okay, let me move to the next example. So this one is another property we can generate with the help of the previous property. So if I have three number of event and their union, what is the probability of their union? So let us quickly do that. P of E union F union, just a minute. E union F union G. Now this proof we can do it with the help of this previous inequality identity. You take this one as one event and this is another event. So this is the union of two events. I can certainly apply that identity. E union F plus P of G minus their intersection. So P of E union F intersection G. Now this one, we already know the value of this one. We know the identity. So it is equal to P of E plus P of F minus P of E intersection F. Plus P of G was there. I'm keeping it as it is. And minus this part, I'm taking it here. So minus, just because minus was there, I can write this one as P of E intersection G union F intersection G, right? Because this is the by distributive law of sets. So I can write down E union F intersection G as E union F intersection G equal to E intersection G union F intersection G. Now if I apply the probability and the formula we already have, it will be P of E intersection G plus P of F intersection G and minus their intersection, it is P of E intersection G intersection F intersection G. And let us close the third bracket. We have this. So if I just simplify, this value is actually G is appearing two times and it is the intersection. So I will get it is equal to P of E plus P of F plus P of G. It was there already minus P of E intersection F minus P of E intersection G minus P of F intersection G, and minus become plus P of E intersection G intersection A, all their intersection. So my point is, in the earlier case we had P of E union F equal to this value. If I have three union, I got this value. P of E plus P of F plus P of G minus two pair you have to take and you have to subtract them. After that, you have to take three altogether their intersection. So alternatively plus or minus. So here all of them are minus 2, they are minus. Here I have taken 3, so they are plus, and initially it was 1 pair. So alternatively plus or minus. So with this, we can certainly generalize this identity, the known as inclusion exclusion identity, and this is the probability of union of n number of events is equal to their individual sum initially minus alternative plus or minus it will happen. So take two pair and take their intersection, so minus, then again plus 3 their intersection you have to take. So alternatively plus or minus, in certain stage you will have r number of intersection, and at the end again alternatively plus or minus, you have to take all of their intersection, and depending on n it will have plus or minus, right? So this is the general inclusion exclusion identity. So I hope you understand. Let me do one more example. Read this example carefully and then try to get the answer of it. It says that in a certain residential area, 60% of all households get internet service from a local cable company, 80% get television service from that company, and 50% get both the service from the company. Now, if a random household is randomly selected, what is the probability that it gets at least one of these two services from the company? Now, what you have to do, you should understand that. Let us denote each of the event by some alphabet. Let A be the event such that that household get internet service from the company. So A is the event that household get internet service, and B be the event that households get the television service. Then what other things are given? Probability of A is given as 60%, so it is 60 by 100, 0.6. P of B equal to 80%, so it is 0.8, and 50% get both the service, so P of A intersection B is also given, which is 0.5. Now, what is the probability that at least it get one of these two service from the company? That means P of A union B at least means. So P of A union B equal to, you know the formula, it is P of A plus P of B minus P of A intersection B. And if I just substitute the value, you'll be getting the answer as 0.9. Now, this question has another part into it. It says that what is the probability that it gets exactly one of this service from the company? Now, exactly one means either the households get internet, or it can get only the television, but not the both. So you should not have that case. So how to solve this thing? Exactly one means, so exactly one means you had, this is the sample space, right? So this was the A event, this was the B event. Exactly one means either you have to take this part or you have to take this part. Correct? So it means A intersection B complement or B intersection A complement. Right? So this part is A intersection B complement, and this means this is the B intersection A complement. So at least what is the word that exactly one of these service from the company. So therefore, probability of exactly one service is equal to probability of, so either A intersection B complement, or B intersection A complement, right? And this is the sum of their probability by axiom 3. So it is A intersection B complement plus B intersection A complement. Now, what is the probability of A intersection B complement? What is this probability? It is basically A minus probability of A intersection B. So it is P of A minus P of A intersection B. Because it is this part, right? So it is A minus A intersection B. And whose value if I put, because everything is given, whose value if I put, it will be 0.6 minus 0.5 equal to 0.1. Again, P of B intersection A complement, if I put, it is P of B minus P of A intersection B. And if I substitute the value, we'll be getting 0.3. And if I put both the values in this, I'll get the required answer equal to 0.1 plus 0.3 equal to 0.4. Right? So the formal answer, where all these things are in detail, you can have a snap of it. You can get the answer here. The first part is this one. And the second part answer is this one. Everything is written here. Okay, I'll quickly go through a few more examples, two more examples. Read the question carefully. If the probabilities are respectively this, and this, that a car stopped at a roadblock will have faulty brakes, badly owned tires, or faulty brakes and or badly owned tires. What is the probability that such a car will have both faulty brakes and badly owned tires? So you just read the question. I hope you can do it, able to do this answer. I'm not discussing this one. I'm just quickly show you the answer of it. First you try. If you don't get, then you can see this answer. So definitely it is the you have to get that what is the intersection of these two events. So therefore I will get the answer is this. Now you do this problem. A total of 36 members of a club play tennis, 28 play squash, and 18 play badminton. Furthermore, 22 of the members play both tennis and squash, 12 play both tennis and badminton, 9 play both squash and badminton, and 4 play all three sports. How many members of the club play at least one of these three sports? So let us denote the events. Let T be the event that they play the tennis. S be the event such that they play the squash. And B be the event that they play badminton. Right? Then what other things are given? It is given that basically it is a cardinality. So because we are discussing in terms of probability, I can write P of T, but basically it is the cardinality of this event T. 36 member play of this plays the tennis. So the cardinality of T is equal to 36. Cardinality of A is equal to 28. Cardinality of the set B equal to 18. Furthermore, 22 players play both tennis and squash. So cardinality of the T intersection S is equal to 22. Cardinality of T intersection B is equal to 12. Cardinality of uh, S intersection B is equal to 9. And cardinality of all of them is equal to 4. Now you know what you have to do. How many members of this club play at least one of the three sports. So therefore, you have to take the cardinality of T union S union B, this value, and by the inclusion exclusion identity, this is also holds for set. You have the formula. If you put the value, you'll be getting the answer. So I'll just quickly show the answer. So this is the formula, and after that you put all the value, substitute all the value, you'll be getting the value is 43. Right? So in the next we'll discuss some probability of equally likely events. So if you enjoy the video, if you like the video, please share your feedback. You can write down in the comment box. Right? Okay, we'll meet in the next video. Thank you very much.